Yeah, then I will start this seminar. My name is Carsten Wächter from University of Ulm. Some may know me as Toxi from Apocalypse Incorporated or Metal Fotze. And I'm talking today about the newest trends in real-time ray tracing, so the stuff that is currently used and is really practical, and then some newer stuff that isn't really released. So it's our work, our newest work, which I also think has a lot of potential, especially if you're thinking about dynamic scenes. So to start off, for those that don't exactly know what's ray tracing all about, so I hope you at least know this small collection of ray tracing demos, which I find the most impressive. So there's the Fresnel series by Color, which uses ray tracing and the graphics board to interpolate between the coarse results they calculate. Heaven 7 uses the same tricks, but in software. Industrial Light and Magic is brute force ray tracing, at least I think so. I couldn't spot any interpolation artifacts. Then the most famous, or which I think the best engine that is currently out there in considering real-time ray tracing. It's not the most modern, it uses rather old algorithms, but it produces the best results. By Federation Against Nature, they also released some benchmarks lately, which even feature real-time global illumination effects. And then of course there's the famous option by Potion on Amiga PPC. But we must say real-time ray tracing in the demo scene is dead at the moment. Nothing is released which is really impressive. There are some small intros, and that's about it. But this is kind of confusing because in the scientific and commercial research, there is so much going on with so much potential in it. And it's a shame nobody uses this information. And I hope I'll introduce you to this world, what is going on or what has been going on in the least 2 or up to 5 years. So what's the principles? In the demo scene, real-time ray tracing is all about hardcore assembly optimizing the standard algorithms that are out there. Then there is a bunch of dirty tricks, not in all of them, but in some. So they calculate a very coarse solution using ray tracing, interpolate between the results. Where the interpolation fails, they shoot some more rays. This is okay, but it's not all you can do. And the scientific community relies on new algorithms. There really has been tons of papers in the last years, and they only use slightly optimized C++ code and sometimes some SSE code for the inner loops. So if we would combine these two, I think it's possible to make really stunning demos using real-time ray tracing. So here also a very brief introduction. You have an image plane, so of the really old style ray tracing, how it was done some years ago. You have the image plane, you have a camera, you shoot from the camera through the image plane the primary rays into the scene. From the intersection point you shoot some more rays, for example for the light sources, for reflections if the material is glossy, and for refraction if it is transparent. So why should one use ray tracing? I mean, there is all these stunning games out there that look almost real. But that's the point. They look almost real. To get that least thing of reality, so it feels real. Not look good, it looks real. You need to calculate the physical solution. And for this you need ray tracing. So you get all these fancy refraction or even subsurface scattering effects, glossy surfaces, and most important, global illumination, which can only be faked very coarse on current graphics boards. So what's also a big point or a big plus, which I think is you don't need to fake things like on the graphics board. You just do it as you think it works in reality. So you don't need shadow volumes or shadow maps or reflection maps, which are never the real thing. You just program it like it's in the textbook with a straightforward recursive formulation. So then there is also the massive scenes, which can be faster using ray tracing as on the graphics board. So if you think in a multi-million ratios, so for example, if you want to visualize a whole Boeing 777 with 300 million triangles, this can be faster on the CPU using ray tracing than on the graphics board. And this is because of the log n complexity to find an intersection point. But this is, I will talk more about that log n complexity later. So why shouldn't one use ray tracing? There is also, of course, some negative aspects. First of all, the algorithms are much more involved than the rasterization effects. You have to do much more work to get a picture, to get the engine running than writing a simple rasterizer. And also it's much more costly because the mathematics behind it are much more complicated, so you can't fake as much as or use cool tricks like in rasterization. So then the biggest negative aspect is you need an additional data structure to get the ray tracing fast. So if you want to find the nearest intersection of a ray with all the triangles, you would need to intersect all triangles with the ray. This is of course bullshit. If you have 1 million rays and 1 million triangles, this will run forever. So you need some data structure to make things faster, to make the lookup of the nearest intersection much faster. I will also go into detail later on. And possible, just as an introduction, are the spatial partitionings like the BSP, KD tree, or regular grids, or object list partitioning like boundary volume hierarchies, or which we found out the bounding interval hierarchy. Also more details later. So a drawback is that you need additional memory for the tree. And here comes the point. In reality, ray tracing is n log n and not log n. So because you have to build that damn hierarchy, and this is basically a sorting algorithm which on the average takes n log n. So this is especially visible in dynamic scenes where you need to construct the tree every frame from scratch. So the log n complexity falls back to an n log n complexity then. So, and if you implement it, there are lots of other evil things. You have less numerical precision. So if you just rasterize the primary rays with a graphics board, you have no holes in the geometry. With ray tracing, you easily get some holes where between the triangles or where the vertices are. You can get rid of that unless you use really advanced algorithms, but then the calculations are running forever. So you also get a loss of cache coherence, because most of the time the rays are totally chaotic, bouncing in a scene. So not like in the rasterizer case where when you draw big triangles, there is perfect cache coherence for that. And there are also a lot of other fancy tricks in the boards by now. Can't do that with ray tracing, not at the moment. So and then you also need a SSE implementation, so not really assembler, but using intrinsics to get the full performance. And this is about a factor 2 to 3 times faster on the latest CPUs by Intel and AMD. And also you want to utilize hyperthreading or multi-core architectures, because this is an additional factor of, in the hyperthreading case, maybe 20 to 30%, and for multi-cores it scales more or less linear, but not for the construction of the tree. This is a bit more difficult. There are some algorithms out there, and we also have some one algorithm running which scales more or less linear, but this is too much to talk about today. So now we start off with the real talk. As I said, there are two types of acceleration data structures out there: the spatial partitionings and the object list partitionings. And the popular one is the BSP, which you might also know from Doom or Quake or whatever. It's pretty simple. You have a bunch of triangles, and you pick one splitting plane, and you look which are left of it and which are right of it, or better to say, which are in the volume left or in the volume right. And this is done recursively, and you get something like this. So you have the leaves where the triangles are, and if you want to find the intersection later on, you go through the tree and look where is the ray in. Is it just left? Is it right? Is it in the both? And so on, until you find an intersection point, and then it's done. So this is suited for all kinds of scenes, even the problematic ones. So this means it's a general purpose tool, but it also has some drawbacks. As I said, the ray traversal is pretty easy, so I'm concentrating on the KD case because BSP is too much for ray tracing, so I'll use its subset, the axis-aligned KD tree, so you can only pick split planes on the principal axis. And if you want to construct it, here are the triangles again. You pick a split plane, look which are left, which are right, and if you traverse the thing later on, you have to distinguish three cases: just going left, just going right, or going through both. And then there's also the ray direction, if you have to visit the left first, or the right first, or the other way around. So pretty easy. But as you already see here, these two triangles will go into both sides. So if you construct a tree, they are replicated. Mostly they're just the indices replicated, so it's not too bad for the overall memory use, but nevertheless they are replicated, and so the memory prediction is slightly impossible. You can just say there's an upper border of n square, but this is totally useless. In reality, this is mostly 6 times the number of triangles, or 4 times, depending on the scene. But you cannot say, I have this scene and so many memory I will use later on. And there is also the precision problems, because if you sort the triangles to the left and to the right, you will need a triangle voxel intersection. Okay, you might say, why do I need that? There's just a split plane. I look, is it left, is it right, or is it crossing the split plane? That should be enough. No, for the later cases, it might be the case that a triangle is, for example, here, and it will intersect the split plane here. But this doesn't matter. It's not in the left half, it's just in the right half, because it crosses just a corner. So this is mathematically involved, the triangle voxel intersection, and it's also very costly to do. So, as I said, you have to choose a split plane. And this is, this is a pretty hard thing to do, because there are the easy ones that are also cheap to calculate, and there are the difficult ones that eat up lots of CPU time. And the easy ones would be, you take the object list and you choose a split such that to the left and to the right are the triangles that go to the left and to the right are equal in size. So if you have 200 triangles and some replications, maybe 125 go to the left and 125 go to the right. Because of the replications, you have 50 more. But this is total bullshit, doesn't work for most of the scenes, so we can simply forget the median. Then there is the split in the middle. You take the current node, pick the longest axis, and split it directly in the middle. Sounds like a good idea, because it's kind of like the way to go for sorting algorithms. But in our case, it's bad, because we will get a lot of replications. So the next idea is to just choose the vertex that is nearest to the middle. This way you won't get as much replications, and you also will cut off more empty space. So this is an easy heuristic that works very well. But are there better trees? Of course, but we have to do some assumptions. So first we assume that the rays we will shoot later on are equal distributed in space, which is also not really the best assumption, but we have to do it to make some formulas. And we must assume that the rays are not blocked by other objects. Also total bullshit, because we want to find intersections. And we have to assume that the intersection and the traversal times for each ray is the same on every depth of the tree. Also totally unrealistic. But nevertheless, we can formulate a nice and easy term here. This is very old. I think it's 15 years old or even 20 years old. But works. There might be better stuff out there, but nobody knows of it. So this is the best we can get at the moment, and which is also used the most. So what is going on? We have the volume of we have some node, and we want to find the optimal split plane. So we pick some split planes. And for each split plane, we must calculate this cost split. So we look how many volume we have on the left, and how many volume we have on the right, and how many triangles will go to the left and to the right with this split plane we just picked. Then we have the cycles a traversal does cost. We have the cycles an intersection does cost. We have a probability. Ja, scheiße, mir fällt das Wort nicht ein. Yeah, we have the probability of hitting of when a ray hits this volume or the right one, and this is all depending on the surface area. So that's why the whole heuristic is called the surface area heuristic. But the problem is, for every possible split plane, we will have to calculate this term here. So for all vertices and all triangle voxel intersections, you will have to sort the triangles to the left, to the right. You have to calculate, okay, this is fast, but getting the NL and the NR is the costly thing. So we get a complexity of n square if n is the triangles in the current node per SAH evaluation. And this is totally nonsense, because even for very simple scenes it will take minutes to build one hierarchy. Or if you have models with 10 million triangles or something like that, you will take days. And this is totally unrealistic. We need something that is done in a few seconds, or for small scenes some milliseconds. So there are some optimizations out there. First of all, I said you have to pick a number of split planes, and you have to sort to the left and to the right for every one of them. But there is some trick which uses some pre-sorted lists for each axis. So you calculate at the beginning some pre-sorted lists, 2 for each axis, and using these lists you can do the whole thing for all split planes in one pass, the whole calculations, and so you will fall back to linear complexity per SAH evaluation. This isn't too bad, but still not the best we can do. So we must reduce the number of tested split planes, so we have less candidates on one axis. So we don't pick any vertex or any voxel intersection. We just discretize the whole volume and pick one candidate from each cell. And then you get a complexity of n through k, if k is the number of discretizations we use. But the bad thing is the tree is not optimal anymore. So sometimes these heuristics can becoming so worse that you rather use a simple heuristic for the same price than using these approximations. Yeah, they are also a hell of an effort to code. You will produce hundreds of lines of code. And it's also much slower to build the hierarchy than with the easy split blank criteria. But this can pay off for the static scenes or walkthroughs. So if you have that Boeing again, and you just want to show the people that will buy it, look here, fancy lighting or whatever, you can construct the thing. Okay, it's running a week or so. Doesn't matter. The customer wants to have the thing fast and interactive. So this can pay off for static scenes. So another thing that is really popular at the moment, it's shaft and bundle tracing. So we want to exploit the coherency basically. So if you think of the camera and of neighboring rays, then you will see that the decisions they take during the traversal of the tree will be mostly the same until the lower levels of the tree. Then they will take different decisions, but on the upper tree, everything will be the same. So we can combine some of the rays into shafts or bundles. So bundles means you take the rays and have to mask some of them out if they take different decisions in the tree. And shafts means you encapsulate the rays into into truncated pyramids, like camera frustum. So same principle, and you trace this whole frustum through the tree. And this amortizes the traversal costs of the rays. And sometimes if you have large triangles in the scenes, you can also save on the triangle intersections. So the bad thing is, for secondary rays, so reflection, shadows, refractions, sorry, the thing gets incoherent again. Because if you think of a sphere and neighboring intersections and the sphere is glossy, the spheres will, the rays will go in different directions, and all your coherency for the secondary rays is gone. Then there is also different materials and shaders you must evaluate. So if you shoot through the camera and some of the rays will hit a sphere and some of them will hit a neighboring cube and they have different materials, you're lost. Because then you have to restore the coherency, introduce even more overhead in code, and have to do some material or shader sorting. And this is also too much. You will lose all the performance you got through the first pass by sorting the second pass. So the guys at Intel have released a paper, the multi-level ray tracing algorithm, that subdivides the shafts and bundles during the first. So if you shoot the primary rays and they take different decisions, they subdivide the shafts or the bundles and try to get more coherency through that. But this is also very complicated, and I don't know if this is all worth it. So now for the new stuff. Some of you might maybe know this already. It's the bounding interval hierarchy, and we came up with this to it's somehow a hybrid between bounding volume hierarchies and KD trees. Actually, it's a bounding volume hierarchy, but it has the fast traversal from KD trees and the linear bounded memory and numerical stability from the bounding volume hierarchies. And additionally, we proposed a extremely fast setup. So the tree construction is super fast compared to the KD trees that are out there. So what is the principle? Here is the KD tree traversal again. Here the bounding interval hierarchy traversal. So instead of one split plane, we have two clipping planes, and they separate the left and the right part. So these three triangles are in the left part, so they have this clipping plane, and these three triangles are in the right part. They have this clipping plane. So the traversal is almost the same, except that you have to calculate two intersections with these clipping planes instead of just one. And there is an additional case. If you have empty volume between the triangles, and that's about it. The rest is the same easy traversal from the KD tree, except for this case here. So super simple. Can be done by anyone who has a KD tree traversal, can pimp this traversal in 20 minutes. So, and then there's the global heuristic I talked about. So, the thing is, I told you about the heuristic for the KD tree, where you have the node volume, and you pick the exact middle of this node, of the volume on the longest axis, exactly the middle. And this was inspired by this, but we don't calculate the middle from the current node we are, but we subdivide the whole scene in advance in equally sized voxels. But only implicitly. We don't store this information or any of that. This is calculated on the fly during the construction. So what happens is, we have the first split plane proposal. We do the sorting left and right, and these two clip planes will come out. Then we continue with the left child. We propose this split plane, results in these clipping planes. The lower child is done because there is just one triangle in there. We continue with the upper part. We propose this thing here, results in this clip plane, and so on, and also for the right side. So super simple. But the good thing is this heuristic works pretty good. And as I said, it's very simple. You just decide if a triangle is going to the left or to the right by the overlap of a triangle. Of course, when it's completely left or completely right, it's easily done. But if it crosses the split plane proposal, you just take the minimum overlap and sort it into that. So then there is, because we use this regular grid here as proposals for the split planes or the clipping planes in this case, we can do a pre-processing, which makes things even faster. So you use a voxel grid, and this can be pretty coarse, so you don't have to spend millions of cells, no, some few thousands are enough. And you use this to do a bucket sort of the triangles. So you pick one point of each triangle. This can be a vertex of the triangle or the middle point of the triangle, and you use that point to sort it into the voxel. Just this point, not the whole triangle, just this point into the buckets. And then in the second pass, you go over all the buckets and calculate the real volume of the bucket. So you go over all the triangles that have been assigned to this bucket and calculate the bounding box of them. And then you use these boxes to construct a final hierarchy. So the cool thing is, if you think about it close enough, this exactly same trees will come out if you use the middle point of the triangles. But you're one step closer to O from N complexity. In reality, it's just a factor of 2 to 3 you will gain. But for such a simple algorithm and a really simple implementation, this is, I would say, considerable to include this. So what are the problems of the bounding interval hierarchy? As each BVH, it suffers from a mixture of large and small triangles. So what does it mean? If you have architectural models, like this room here, you have big walls with a small amount of large triangles. And you have some details going on, like the pipes and stuff. And the mixture of these both are bad for BVHs, because the volume of the nodes will explode, and the KD can solve this by voxelizing the triangle. So it will split and split and split, and will build small blocks on the triangles to cut off the empty space around them. But for all real-life scenes, I would say, or scenes that are now out there that are highly tessellated, the BIH always outperforms the KD. Not only in the pre-processing time, so the tree construction, but also during the ray tracing phase. So now for the implementation. These were just the algorithms. Now we also have, so this is the really new stuff. This isn't released or anything, so you're the first to hear it. If you have the standard recursive hierarchy built, you first, because it's a recursion, you have to define a termination criteria. So when does all this stuff stop? So if a node has a pretty small volume, you might consider, okay, let's create a leaf. If it has only a few triangles, like 2 triangles in them, make a leaf. Or if the depth is, for example, if the tree depth of the current node is bigger than 50 or something, you might create a leaf. So these are the standard criteria that are out there. Then you do a split plane selection. So where will the node be splitted? So you use the SAH or our global heuristic or some of the easy heuristics. Then you do a classification, so which triangles will go to the left or to the right, or in the case of the KD tree, which are going to both. Then we create the node, and this is done recursively until all leaves are created. You can do some optional optimizing of the tree, but this is most of the time overdose, especially if you have dynamic scenes. So what are the problems? The replications that happened for the KD tree are very difficult to handle in place. So you have to do some very, very ugly memory management. So all the triangles that are duplicated during a split have to go to some kind of stack. So then you continue with the left one, with the triangles just going to the left, plus those that are on the stack. And you have to store these on the stack for the right child, because you first do the left subtree, and for the right subtree you also need the doubled items. And this is all very ugly, and you will need lots of temporary memory. And additionally, as I already said, the total memory is totally unpredictable for the KD tree, and resulting from this also is the build time complexity is nearly impossible. So you don't know how long will it take to construct a tree. So what we propose is, this is the start. So you have a memory block, for example 500 megabytes, because you just want to spend 500 megabytes for the tree if you have a very large model. And you put all the references to the objects, so for example for the triangles, into the first part of the list. So there will be 0, 1, 2, 3, 4 until n minus 1. And you have a free memory block. So then you continue. For the first split you do, you will sort the left to the beginning. The unclassified are still here. So at the beginning, these are all unclassified. You put them to the left, to the right, or to the left and right. This can all be done in place and is more or less simple. The implementation is a little bit tricky, but if you if you make some thinking about it, it's pretty easy. So and then you will come out with 2. So here you have to spend additional memory for the 2 nodes you will create for the 2 children. So there will be the split planes in there and the pointers. And then you have to predict the memory for the left child and predict the memory for the right child. So all the stuff that goes to the left will be, for example, up to here, and all the stuff going to the right will be up to here. Then the left and right are copied behind them, and then there is still some free memory left. And then it goes back to here, where you have the reference to the objects and some free memory, and this continues and continues and continues until you have no more free memory left. So you have the perfect balance of the tree. You don't need any fancy criteria so where the termination is. No, you just say, if I don't have any more free memory, then it's okay, I'm done. And you use up the space, I would say optimal. And you can also limit the memory. If you just have 100 megabytes, because all the textures will eat up the space, no problem, will still work. You just have to give enough memory that the reference to the objects fit into this memory block plus one node at the beginning. So you can create the root node plus the references. And everything that is more than that just helps to get a better tree. So for the prediction, you still have to predict how many memory the left child gets and how many the right child gets. Of course, you have to give them both enough to fit the left or the right into them. And you can just do the ratio, how many triangles have gone to the left and to the right. And with this ratio, you can choose this border here. So very simple. And you need no temporary memory. That's the good thing. And so here just another thing you could do, you could also store them in pre-order. So you don't have the two nodes at the beginning, but at the beginning of each subtree. So the right node will be here instead of here. This is also possible without any problems. So the algorithm changes to this. All the other criteria can be thrown away. Do we still have free memory? If no, create a leaf. Then the rest is the same, and here this memory prediction step, you can choose your own heuristic, whatever you like. You could even base this on the SA8. So super simple. And you also get some post-processing for free in this step for the KD, but I can't go into details. So we have some solutions for the problems I told on the last slides. The replications are totally easy to handle because you just have this left and right. And as you have to copy them anyway, because they will be in the tree later on, everything's perfect and everything's running in place. So you have no temporary memory, really absolutely no temporary memory. You give this block and this is all the tree will use. Nothing more, just a stack, of course. And you have full memory control. You can limit the memory to any size you want. And what we also found out through this memory limitation, you can also predict the build time. So if, yeah? No?
Okay, you say you have to make some prediction how many child nodes go to the left or to the right. Can't you just fill the memory like from the outside in? Like start at 0 plus 1, 2, 3, 4, 5 for left nodes and n minus 1, 2, 3, 4, 5 for the right nodes until you meet somewhere in between?
Yeah, this is possible. So you just fill them from the left and to the right. Yeah, this is also possible, but then the termination criteria is kind of crashed because the left subtree will eat up all the memory because with the recursion you go the left subtree down, it will just fill all the memory and the right tree is fucked because it hasn't any memory at all.
You could traverse your trees breadth first instead of depth first?
Yeah, but this is much more complicated. if you do it breadth first. Of course, it's an option, but I think it's much slower because the implementation is much more complicated then. But of course, it's an option, yeah. Okay. As I said, the build time is now predictable. So you can, it's not totally, you cannot say it's exactly that build time because you cannot say what happens during the tree traversal, how many replications you will get, so how many time is spent in the triangle voxel intersection and this stuff. But you can roughly say, if you have some measured values, you can easily extrapolate these values and get the time. So for dynamic scenes, this is kind of like perfect. So and then there is also something that is in the literature for, I don't know, 30 years, but nobody uses it because it is a hell to code. It's the on-demand construction. So what does that mean? You only build a data structure where rays are really shot. So if you have this immense city and you're just sitting, okay, and you're just sitting, I'm almost done, and you're just sitting in one room. So why would you want to build the whole city? It's totally nonsense. So you have to think of something that just builds the hierarchy where you're at. So first of all, you have to map the recursive build to an iterative version. So this is pretty easy with our algorithms because you start with the full scene bounding box with all triangles in it. You shoot the first ray. You have to make the first split. Then you stop. You store all the temporary information you would else need for the stack. So you would need to continue to the left, to the right. They both need some information. How many triangles are in there? What is the bounding box? And you just store this here at the end of the references, at the first bytes in your free memory. And so it's no problem at all. You just continue with the ray. He's going just to the left, continue with the left. He's doing both, continue with both. But you can leave the other unfinished stuff just as it is. And if other rays need to traverse the other sides, no problem. You have to stack the information there. So this is the manual stack handling I was just saying. And you also have no temporary index lists anymore. Because this was giving the researchers and the coders headaches. It's really hell to code with on-demand construction. Now this is all solved. It's so simple. You just need, it's really 10 lines in the code. And you have the recursive build mapped to the on-demand construction. And this is much, much faster than constructing the full tree. Especially if you have the scenario of the city and just sitting in a room. And it also helps for all dynamic scenes. So for games, to construct just the part of the tree you really need. And it's really simple with this. So what you can take home. I hope some of you are inspired to make the first really good looking RTRT demo. No offense, but we saw enough of the spheres and cubes. Maybe it's time to do some more complex stuff. I mean, the Federation Against Nature guys already did something really impressive, but I think with the newest algorithms that are out there and were released, I mean, this is just a small subset of what I think is interesting at the moment or what has potential. If you use these technologies, there is much more. And also you still have the option. You can still do the old interpolation or graphics hardware tricks or even use the graphics hardware to shoot some rays or whatever. The only thing I'm a bit skeptic about is the shaft tracing. It's okay for primary rays, but if you can just do it for primary rays, why don't render the primary rays with the graphics board? It's good at it. And then just do all the secondary stuff with real ray tracing. And there's some advertisement. You can get a BIH paper at our homepage and a tech report with the latest stuff. at the end of this talk, and also some stuff I couldn't talk yet about. Some other cool tricks will be in a tech report, I think, in 2 weeks or so on the homepage. And also thanks to Mental Images for funding our research. And that's it. Thanks. Have we still time for questions, or okay, anyone? Okay. Is this good or bad?
Question.
Huh? Oh, will we be able to get your slides as PDF or something?
Yes. I can give them to the organizers and they can put it up somewhere. I hope so.
Oh, cool.
Yeah.
When you dynamically construct during the ray trace phase, you build a tree. Doesn't that cause a lot of cache misses, page faults, page misses, because you're running two different algorithms on different areas of the memory together?
No, it's not really on different parts of the memory. This is the cool thing. If you would construct a tree, you would have all these cache misses anyway. Because you go to the left side and then somewhere you have to jump up and pick the stuff from the stack and so on and so on. So cache misses anyway. And this way you have less cache misses because you just traveled there where you need to. And the race that will follow, if they are almost coherent, they will travel the same path as before and will touch triangles that are already in the cache. So because you don't build the full subtrees anymore, you're just building that what is really visible. So I did some experiments building the full tree. Also I designed the scene that way that every triangle will get hit by some rays. And this was faster doing the on-demand construction than doing first the construction and then the ray tracing. I don't know exactly why this happened, but it must be something with the caches because they are better utilized then. Okay. I'll wait for the microphone.
When you are rendering the next pixel next to the other pixel, then you have a high chance that the same path on the tree will be traversed. So is there a way to cache the path so you don't have to start from the root node but from the leaves?
Yeah, there is some in the paper by Intel, the multi-level ray tracing algorithms, it tries to do that. So you have a bunch of rays and try to find a entry point for all of them. So you just have one traversal for all for all rays, and then when they are diverged in the tree, then you start with the single rays included. So this is kind of like resembling this idea, but otherwise it's kind of difficult because you could use the cached traversal, but you have to look if it was really the right way you traverse, because you don't know if this ray will traverse the exact same way. So you have to do the calculations anyway. So it's difficult to make this right. You can just guess that it's the same traversal, but there is some phase in the algorithm that has to correct eventual errors, because the prediction will never be right. Can't be, because otherwise you could draw the picture without ever tracing a ray. Okay. Yeah, thanks.